Thank you very much for the kind introduction. Let me directly start with the motivation of this project. So multi-slice viricity is a standard procedure in modern clinical diagnostics, and the characteristic feature is the spiral trajectory, which is caused by continuously advancing the patient through the gantry. However, a difficulty is that during the back projection, an interpolation is required in between of adjacent detector rows. By not satisfying the Nyquist criterion here, this can lead to so-called windmill artifacts. Here you can see an example of this. These image distortions are characterized by streaks diverging from high contrast edges. And if you scroll through the affected slices, they appear like they show the impression of a rotating windmill, hence the name windmill artifacts. There are several ways and methods to counteract windmill artifacts. The most straightforward method would be to just reconstruct thicker slices, usually up to or more than 2 times the acquisition thickness. However, this would lead to a reduction of resolution in Z direction, would appear as blurring in the reconstructed images. Other previous works focus on the reduction of windmill artifacts in the image domain, for example, by total variation minimization or other methods. But nevertheless, state-of-the-art windmill artifact reduction is provided by a hardware-based method called the Z-flying focal spot. Here you can see a comparison of 2 scans. On the left-hand side, you can see the scan of a Siemens Somatom 4 scanner acquired without the Z-flying focal spot, and you can clearly determine the streaks. And on the right-hand side, you can see a corresponding reconstruction of a scan where Z-flying focal spot was enabled. Here prepared some other slices just for comparison. Also here you can clearly see the difference. So let us quickly have a look on how the method actually works. So the ZFFS allows for the periodic movement of the focal spot in longitudinal direction to improve the sampling in the Z direction. The electron beam, so by electromagnetic deflection, the electron beam is alternating on the anode surface, and the movement is set so that 2 consecutive measured detector readouts are shifted by half a collimated layer width in Z direction. This basically doubles the sampling. So if you have, for example, 96 times 0.6 collimated detector rows, you will achieve 192 detector rows with a sampling distance of 0.3 millimeters. However, this technique is only provided in high-end CT scanners. And another point is that by using the Z-flying focal spot, an increased number of detector readouts is required. So this may prevent switching in the faster scan mode of the scanner. And this leads us directly to the primary target of our project, to provide a software-based approach that upsamples the projection data like the Z-flying focal spot. And as this is kind of a riddle for our research, we use it as our acronym for the row interpolation with deep learning. Here you can see the basic network structure that we use. So in total, it is a convolutional network, the riddle CNN, which learns a mapping from projection data without the Z-flying without Z-flying focal spot rows to corresponding ZFFS-like rows. After the network prediction, the network and output just need to be interlaced to achieve an upsampled version of the input. And compared to the results that we presented last year on the fully 3D, we reduced the network complexity here. And beside a clinical data set, we introduce here an experimental synthetic data set for network training. Advantages of synthetic data would be that any amount of training data with different structures can be simulated, and this also noise-free. And another point is that no CT scanner that allows for Z-flying focus spot is required for network for training data acquisition. On the bottom left, you can also see how an example of how the training patches were generated from corresponding projection from the clinical data set, and how the network input and output was selected. Let's now go through the individual training data sets. The clinical data set consists of projection data from patient spiral CT scans acquired with Z-flying focus spot. Here we had 40 patient scans, whereas 32 scans were used for training and 8 scans were used for validation. They're basically covered head CT scans, also thorax examinations and abdomen scans, and were equally distributed in the training and validation dataset. And for the synthetic dataset, we used simulation software tool, CTSim, to simulate projection data suitable for the network training. Here we simulated a water cylinder parallel to the z-axis containing 100 randomly arranged spherical shells with varying densities from 0.5 to 3 grams per cubic centimeter. And every of these spherical shell was then overlaid with another smaller shell, resulting in small circular edges with a width of 0.3 to 2 millimeters. And here on the bottom, you can see an example projection from the simulated data set. All in all, we simulated 200,000 noise-free projections, whereas 160,000 were used for training, 40,000 for validation, and the value range of synthetic projection data was linearly scaled to the value range of the clinical data set. Let's now continue with a few training data details. So all in all, we trained 2 different networks, once with the clinical data set and with a noise-free synthetic data set. For both networks, we selected we generated 500,000 examples from the corresponding training data set and 125,000 examples from the corresponding validation data set. We used a combined loss function consisting of pixel-wise loss function consisting of the mean absolute error and the structural similarity index. The initial learning rate was set to 1 times 10 to -5, and yeah, we used an early stopping regularization as well. Yeah. For the evaluation of the windmill artifact reduction, we used 2 scans of a head phantom scan with real human bones, scanned with a Siemens Somatom Force scan. The first scan was acquired with a collimation of 96 times 0.6 millimeters and with Z-flying focus spot enabled. So these were our ground truth data. And the second scan was acquired with another scan mode with a wider collimation of 48 times 1.2 millimeters. And due to the wider collimation, it is more prone to windmill artifacts. Other than that, this scan mode does not allow to enable the Z-flying focal spot. So we had no ground truth data in this case, and the image quality could only be compared qualitatively. So let me now show you a few results. On the left-hand side, you can see the ground truth reconstruction of the projection data acquired with Z-flying focal spot. Next to it, what is titled without ZFFS, we basically replaced every second row of the projection data with the linear interpolation, which should be equal to omitting the Z-flying focal spot from the ground truth data. Then we also replaced every second row with the network trained with the clinical data and also with the synthetic data. And what you can see here also in the zoomed in sections is that the results on the right-hand side of the synthetic, the network that was trained on synthetic data provides the best correlation compared to the ground truth data. This is also underlined by the calculated error measures here. And also if you have a look on the difference images calculated to the ground truth data, you can also see that the results for the network trained with the synthetic data leads to the best results here in this comparison. This can also be seen here in another slide out of this reconstruction. And also in this case, you can see that the network trained on synthetic data could provide the best reduction of windmill artifacts. The results on the second scans are also very promising. So here, as I mentioned before, we didn't have ground truth data as we could not enable the Z flying focal spot. However, you can see also here that the network trained with synthetic data could provide the best reduction of windmill artifacts compared to the results on the network that was trained on clinical data and to the ground truth, or not the ground truth, but to the weighted filter back projection acquired without Z flying focal spot. And here are so another 2 slides where you can clearly determine the results that the synthetic data provides superior results compared to the clinical data set and also to a standard weighted filter back projection of the projection data. So the question is, why are the synthetic data performing better? So in this case, we did a comparison of just the detector rows or just the projection data that was predicted by the networks compared to the corresponding projections out of the ground truth data. And what you can see here qualitatively is that the result of the network trained with clinical data leads somehow to a smoother result. This is also can also be seen quantitatively by a lower standard deviation in the ROIs that we calculated here. And it seems that our network here also performs kind of a denoising due to the different noise distributions presented in the clinical training data. So this would be one hint why the network with trained on synthetic noise-free data provides better results compared to the clinical data. And further, if you have a look on the bottom images, you can see that there's a different structure of the projection data in both data sets. So the synthetic data projections contain significantly more structures over the whole projection compared to the clinical projection data. So let me just conclude our work here. So the proposed method, we could show that the proposed method can reduce windmill artifacts, and other than that, does not require additional hardware. We reduced the complexity of our network architecture in this case, and also provided a noise-free synthetic data set. And we could show that the riddle CNN trained with noise-free synthetic data could reduce windmill artifacts more effectively than the corresponding network trained with clinical data. Inferior results of the clinical data may be attributed to the quantum noise in the clinical data set. And for the outlook, also a more detailed evaluation of the network results on clinical patient scans should be done. And this is what we are currently doing. And also an improvement of the synthetic data set will be done in further steps. So with this, I would like to end my presentation and thank you for your attention.
Thank you. Go ahead.
I was trying to run a FPP in my head of that projection that you have of the synthetic data. Do you have an image of the phantom? Or
Yeah.
Do you have an image of that?
I do have, but unfortunately not here in my presentation right now. But I could provide to you.
My intuition is failing, so I wanted to see that.
Maybe what I can do here.
Yeah. Next question, please.
Hi, thank you for a really interesting talk, and I thought the results were really cool. I was interested in hearing a little bit more about like if you notice any qualitative differences in the performance of the network trained on the clinical versus the synthetic data set in terms of like generating the interpolated rows. And I was also interested, sort of as a general follow-up, if you had compared to a baseline that is using like nearest neighbor interpolation instead of linear interpolation on the detector rows.
Again, the last part, sorry.
If you had used nearest neighbor interpolation instead of linear interpolation on the detector rows.
You mean for the comparison in our no, there we just used the linear interpolation, but basically why we even do it is it is quite difficult to line up the Z positions of the scans, right, for corresponding comparison. But what we also did is we had like two corresponding scans, one with the Z flying focus spot enabled and one without, and also in this case we could see that the network trained with synthetic data could also reduce the network the windmill artifacts there. Yeah.
Hi, very interesting talk. My question was more on, have you studied more the effect of the patch size since it's a patch-based method versus not using patches on the whole image? And then like, have you done any studies, ablation studies with the architecture of the network? So those were my questions.
Not yet. We started with training with the patches just because it was more convenient, because of training on the whole projection data would require just more memory also. Yeah, and yeah, but this is definitely a point where we are also working on. Yeah.
Okay, thank you.
You mentioned very early on that a higher frame rate could also help reduce the artifacts. What kind of frame rate are we talking about?
Did I mention again? Sorry, I didn't.
Very early on in the beginning of the talk, you mentioned that a higher frame rate could also reduce artifacts. Like reduce acquisition time, take more images.
Yeah, no. What I was saying is the higher sampling just reduces the artifact. I don't know the higher frame rate.
Okay, so what would you do to increase the sampling?
Basically, the sampling is due to the shift of the focal spot. We have just a more dense sampling in Z direction, right? So, for example, if we have 0.6 millimeters, then we have 0.3 millimeters sampling, and due to that, we can reduce the windmill artifacts. But I don't. Maybe I.
Yeah, no, maybe we
question.
Need to discuss this offline.
Maybe I can clarify, because Jan mentioned the frame rate, because when you switch on the flying focal spot, you have to do two readouts of the detector in order to get one projection, basically. So if you want to have a very fast scan mode, it might be that the vendor does not enable the Z flying focal spot in order to allow the very fast scan modes.
Oh, I see. Okay, thank you.
So thank you for your talk. Very interesting. I have a very small question. So since you found out that the training with the synthetic data is actually performing better than the patient data, I was wondering if you thought about using both data sets at the same time. So first, for instance, training with the synthetic data set and retraining with the patient data set from the clinic.
Mm-hmm. We thought about that. We are, for the current state, we don't know how actually to implement this. We thought about also a denoising step by training with the clinical data set. Could be possible solution, but yeah, we also were thinking how to maybe pre-train or just train on clinical data and also
There's also the possibility to maybe retrain only certain part of the network.
Not yet, but
Not
yeah,
yet, but yeah. I mean,
it's a nice
it's
idea.
in discussion,
Yeah.
of course. Okay, thank you.
Thank you. So let's thank the speaker again.